This is Unit 4, Lesson 5, Part 2. So in Part 1, we learned what complex numbers actually are. We did some operations with them. Now we're going to kind of classify, talk about properties, just really get to know this set of numbers so that we understand what categories these different numbers will fall into. All right, so we are going to adjust this Venn diagram. So we did this in maybe like the very second lesson that we ever did is we looked at this. Now we're expanding this a little bit to include the complex numbers. All right, so we had said before, I'm gonna fill this in, all of these were real. Okay, so we use this capital R for the real numbers, and then we looked at the subset. So within the real numbers, you could either be irrational, squeeze that in, we use an I for that, or it could be rational, and rational has a whole bunch of subsets in here. So remember, for rationals we used a Q. Then within the rationals, the next subset that we have were the integers. So integers were like rational numbers, except they could only have denominators of 1. So they're like not fractions or decimals, but they could be positive or negative. We use a Z for the integers. Then underneath that, we had the whole numbers. So the whole numbers were like integers, except they couldn't be the negatives. Okay, so just like 0, 1, 2, 3, etc. We use W for whole. And the smallest subset would be the natural numbers, which is super similar to the wholes. It just doesn't include zeros. The natural numbers are just 1, 2, 3, 4, 5, etc. So now an even larger group that encompasses all of these, that's the one we just learned, the set of complex numbers. And we use a C for complex. And then there's this other teeny little value right here. These are the pure imaginary numbers. So these are the ones that don't have a real part at all. They just have an I, so like 2I, negative 3I, something like that. So we're gonna use this diagram to classify some numbers. We're gonna look through the odds down the rest of this page. So we're gonna simplify and then we're gonna name all the sets. So we've done this activity before, way back in Unit 1. We just haven't included the complex or the imaginary numbers before. So number 1, we simplify this square root, so the square root of a negative 64. The negative means it's going to be an I, and the square root of 64 comes out as 8. So this simplifies to 8I, and then we can classify it. So everything is complex. It might not be real, but everything is complex. So we can always start there. And then you want to look at subsets. So is it imaginary? Is it real? This one is not real because it's just this 8I. This is actually a pure imaginary number because it isn't attached to a real part at all. So this falls in the complex and the imaginary. So those are our two sets. Number 3. Number 3, the square root of 1/9. It's not a negative, so it's not imaginary. It's just a normal square root. So the square root of 1 is 1, square root of 9 is 3. So this comes out to be 1/3. Okay, so like I said before, everything is complex. Then from there, is it imaginary? Is it real? This one is real because there's no I attached to anything. And then once we decide it's real, we decide is it irrational or is it rational? And 1/3 would be rational. And then keep going down the subsets. Is it an integer? Integers, remember, are not fractions or decimals. Since this is a fraction with a denominator of 3, it's not an integer. So we actually stop there. So it is complex, real, and rational. Next, number 5, we're going to simplify this, which means we FOIL it out. So FOIL 4 times 9 is 36. Outside, 4 times 5I is 20I. Inside, negative I times 9. And last, negative I times 5I would be a negative 5I squared. So remember, just like we saw in the last couple lessons, every time that you come across an I squared, you take this and you replace it with a negative 1. So combining like terms, we have 36 minus a negative 5, so 36 plus 5 would be 41. And then 20I minus 9I would be 11I. So this is what it simplifies to. When we're categorizing, we know it's going to be complex. And then beyond that, we want to see, is it pure imaginary? Is it real? And it's actually not either. Pure imaginary means it wouldn't have the 41. Real means it wouldn't have the 11I. So it's not imaginary or real, it's just complex when it's got both parts like this. So just the one category. Number 7, we'll clean this up. So start with the exponents. We cube these. So negative 2 cubed gives me negative 8. I cubed and then times when I square this. When I square the I get I squared, and then when I square the square root of 7, that gives me 7. So I can clean a couple things up here. So first of all, the negative 8 times 7 would be a negative 56. Remember, I cubed from a previous lesson ends up being negative I. I squared is a negative 1, so I can multiply all that together. So negative times negative times negative ends up being negative, and then it ends up being a 56I. So negative 56I. So let's categorize. Everything's complex. Is it imaginary? Is it real? This one is imaginary because it doesn't have a real part here, the way that this one had the 41. So this is complex and imaginary, and then you stop there. If it's imaginary, it's not real, so it can't have any of those subcategories. Last one, I to the 16th. We did this in the lesson where we learned about the imaginaries, where we break it down into either a real number or an imaginary. So I to the 16th, remember we want to see how many multiples of 4. So I to the 16th already is a multiple of 4, so we can break it down like this. I to the 4th, 4 times. So remember, I to the 4th is just equal to 1. So we have 1 raised to the 4th power, which is just 1. So that's just like a normal number. It falls into a lot of those categories. So we know it's complex, and then is it imaginary or real? We know that it's real. Next subcategory, is it irrational or rational? Hopefully we know that that is rational. It is also an integer because it's not a fraction, or I guess it's not a fraction with anything other than 1 over 1. It is a whole number because it's positive, and it is also a natural number because it's not 0. So lots of categories for that one. So that's our classifying numbers section. We are also going to take some of the properties that we learned for real numbers and expand them to complex numbers. So on the back, I'm going to walk you guys through all of these properties here. So the commutative property, remember that was the one that said that the order can change and it's still okay. So the commutative property of addition, if we had something like this, like 3 plus 4i, is the exact same as 4i plus 3, right? Like we can change the order, and that's technically the exact same number. We could have something like the associative property of multiplication. So the associative property is the way that things are grouped together. So we could have the number 2 times the number 3 times the complex number 4 plus 5i. So those are 3 complex numbers, technically, multiplied together. Let's say I want to group them like this and multiply those two together first. It's the exact same as having 2 times 3 times 4 plus 5i, but let's say instead I want to group these two together first. That associative property tells me I can group them any way I want. Number 13, the distributive property. We definitely know how that one works. This one says if there's a number on the outside, and then an expression on the inside. Notice that's a complex number. The distributive property says we take this and multiply it to both pieces. So 5 times 6 is 30, and then 5 times negative 7i would be minus 35i. So that's a pretty easy one. We actually did that already with this stuff. The identity property, that means that when you multiply, in this case, or add, if we did addition, you'd end up with the exact same value back. So let's say we took a 7i. The identity property of multiplication means if you multiply it by 1, it stays the exact same. Of addition would mean adding 0, and it stays the exact same. And finally, the inverse property of addition, you want two things that add together and give you 0. So let's say I had 3 minus 8i. That's a complex number. If I add negative 3 and a positive 8i, everything would cancel out, and I'd end up getting 0. So this is the additive inverse of this, meaning when I add them together, I get 0. All right, so that's just an example of some properties. You could also have commutative multiplication, associative addition, the identity property of addition, or the inverse for multiplication. We could also have any of those. So let's write down some of these properties. So we are going to do the evens down the rest of this page. So this one, name the property. You've got a 2i on the outside right here, and then on this side it looks like the 2i has been multiplied by both of those pieces. And so that means that that is the distributive property, where you take that 2i and multiply it by both of them. So that one should be fairly easy to recognize. Number 18, this one, it looks like we've got addition. And if you look, the order is the same. It's just the grouping that's different. So the order doesn't change, which means it's not commutative, but the grouping changes, so that's associative. So this is the associative property of addition this time. Up above we saw multiplication, but this one is addition. Number 20, you can see this one's multiplication. And if you look at the order is changing. Like we have this thing, and they swap their position. So if the order is changing, that means it's the commutative property. But this time it's multiplication. Okay, number 22, we are going to name the additive and multiplicative identity of 6i. Okay, so the identity, that's something that will not change the value. So additive identity means what can I add to it and not change it. So the only thing you can add and not change is 0. And then the multiplicative identity, same sort of idea, except this time you want to multiply and not change it. So the number you multiply by without changing is 1. So that's always the additive and multiplicative identity. There's nothing special about the 6i. Let's do this one too so we can have a little practice with inverses. So additive inverse means what do I add to this and end up with 0? So let's write that down. So what do I add to it and end up with 0? So we want these things to cancel. So a negative 8 means positive 8, and a negative 3i means positive 3i. If I were to add these two together, I'd get 0. That's what the additive inverse means. Multiplicative inverse means when I multiply them together, I get 1. And the multiplicative inverse, another thing that we can call it is the reciprocal. So reciprocal just means it's 1 over negative 8 minus 3i. Notice you're not changing this, you're just literally flipping it to its reciprocal. That way when we multiply these together, they would cancel and I would just have 1. That's what the multiplicative inverse means. All right, last section here, we are going to talk about closure with these first couple problems. So we did closure way back in Unit 1. So we're going to see if these are true or false. So the set of complex numbers is closed under addition, meaning if I take complex plus complex, it's always complex. And that is definitely true. Every single number ever is complex. So that means that if I add two numbers together, it will always still fall under that category because every number falls under that category. The next, even number 26, all complex numbers are pure imaginary numbers. That's not true. Even just on that previous page, we saw one like example 5, example 3, example 9, all of these. So like this is not pure imaginary, but it is complex. This is not pure imaginary, but it is complex. Same thing with number 9. So let's actually use this as our counter example, 41 plus 11i. So this is false. And our counter example we're using from the previous page, 41 plus 11i. It's complex, but it's not pure imaginary. And let's look at the last one here, number 28. The product of a real number and a complex number is a real number. Okay, so if I take a real number and multiply it by a complex number, I get a real number. And we actually have a good counter example for that up in number 13. So this is not true. This is false. And if we look up at number 13, I took a real number, multiplied it by a complex number. I do not get a real number. So I'm just going to copy that down as my counterexample. So real times complex, I get something that is complex. It is not real.